Hi all, my name is Sohvi Virkkula. I'm a research scientist at VTT. And we have a very fancy title for the presentation today, but in general, I'm going to be talking about interoperability in these two projects, Independent and Resonance. And let's start with the short introduction on the projects. My presentation is a slightly more technical one, so I hope everyone still has some energy left for that. But as we've all talked about today, demand-side flexibility is essential for the power balance in the system. And in these two projects, we're specifically focusing on buildings and how buildings can be used for this demand-side flexibility through heating, cooling, PVs or EVs, for example. And in the projects, we're applying common standards. So we have the customer energy management standard, as well as the aggregator energy management system standard. And then for semantic interoperability, we're focusing on the SARF ontology and the different suite of SARF extensions as well. And the main goal in the projects is to develop a platform that is plug and play. So essentially, it'll consist of standards-compliant interfaces, both for buildings and industrial sites, and then for aggregators as well. And here's an example of the platform that we're developing in Independent. So we have the two main modules. So we have the customer energy management system and then the aggregator energy management system. And the customer energy management system focuses on building level management. And within the SEMS, we will have specific resource managers that will focus on controlling the actual resources. So those can be things like HVAC, PVs, anything that can be classified as a controllable resource. And then in the module, we will also have semantic adapters that will then provide the interoperability between the actual resource and the corresponding resource manager. And then here we will also have automated resource modeling and optimization for the resources as well. And then within the aggregator module, again, a standardized interface for the aggregator. In here, we will have probabilistic forecasting tool for demand and price forecasts, and then also multi-market interfaces and bidding for energy market participation. So then the main beef of this presentation will focus on the semantic adapters and how we are producing those to provide interoperability within the system. So the goal of these semantic adapters is to provide the interface between the energy resources and the actual resource manager, or it can also be any external data resources like weather forecasts, for example. And here we are building on top of the background work that we've done in Resonance. So in the Resonance project, we developed a semantic resource interface that consisted of a specific resonance ontology that was pilot-specific and a pipeline to semanticize the resource data into this resonance ontology. But in this work, we realized that a framework like this is quite rigid and it's demanding to implement, as each pilot or each resource will require some manual adoption and manual preparation to actually be able to have everything semantically aligned. So now in Independent, we are taking an approach of trying to automate this semantization and integration through large language models. And the goal or the main idea is to use large language models to generate these semantic adapters, and in that way reduce the workload required to actually integrate any of these new resources or new systems into our resource managers and into our SEMs. And again, that's kind of like the main motivation behind the work that we're doing to kind of reduce this barrier of integration of new systems. And now comes the really fun technical part. So I will present the large language model-based tool that we're using to generate these semantic adapters. And the tool is being developed within the Finnish pilot. And so I'll talk a little bit about the Finnish pilot first, and then what is the current status of our LLM tool. So within the Finnish pilot, we're working with a medium-sized supermarket, and it has integrated HVAC, so also has refrigeration, and there's also PVs on site. And the heating system within the pilot consists of a heat pump, and that utilizes a ground thermal valve. There's also floor heating, and then there are, I think, 2 hot water tanks for excess heat capture and for utility water. And in the site, we have a deployed customer energy manager, and then we have resource managers for the HVAC and for PVs. And at the moment, the tool is being developed specifically for this HVAC resource manager. And the main goal would be eventually to have the semantic adapter that connects the supermarket building management system to the HVAC resource model, where we have the optimization model running that will then optimize the heating system of the supermarket. And the supermarket building management system will produce raw data that the semantic adapter will process, clean, and align semantically, and then that can be pumped into the resource manager and directly into the optimization model. And again, the main idea of the project is to use this LLM tool to automate the generation of these semantic adapters. Because again, as many of you know, trying to integrate a new resource into an optimization model or a data platform, it takes a lot of work. It's very costly, requires domain expertise, and it can be very, very time-consuming. So this is our approach to kind of address that issue of integration. So in our LLM tool, we have 4 main capabilities that we want our tool to be able to perform. So first of all, we need to have a way to actually map what the resource endpoints are into our optimization model features. So from the building management system, we need to know which specific data point or which specific sensor is, for example, measuring the indoor temperature in a specific room. So that needs to be able to map into the actual optimization model. Then we also want to map the resource and the model into the SARF ontology to provide overall semantic interoperability across all of our different SEMs and different sites. Then we want our tool to be able to generate Python pre-processing scripts that will actually then be used to fetch and process the data that the optimization model will then ingest. And then finally, we want the tool to be able to generate scripts for an open API service that the model can then connect to and actually get the data and to expose it. So these are kind of like the 4 main capabilities that we have lined for our LLM-based tool. And we have a general architecture for the tool. So we've decided on this supervisor-based architecture where we have a supervisor agent that is managing the overall workflow of the tool and communicating with the engineer or whoever is using the tool. And for each of these specific capabilities, we will have a sub-agent so that it'll stay focused on this one specific task. So we will have 2 types of mapping agents. Again, one that will map the resources into the model, one that will perform the semantic interoperability tasks, so mapping into SRF, and then 2 agents that will utilize code generation, one just for pre-processing scripts and one to generate the open API service. And we decided on this just because it's easier to break down a workflow into these specific agents, because it'll keep the whole tool and the sub-agents more focused into the specific thing that they're trying to do without kind of like overcomplicating the whole thing. And now, as like a final thing, I will show a quick example of one of the agents that we have. So this is the mapping agent, the one that actually maps the resource endpoint to the features of our optimization model. And for this specific agent, we need specific types of inputs for it to be able to do the process. So what we need is some type of context of the actual optimization model. And what we're using in the Finnish pilot is a model configuration file that will have descriptions of the features that the model is actually using. So things like outdoor temperature, indoor temperature. It'll have resolution, units, things like that. Then we will also need information from the actual site. So what are the resource endpoints? And obviously in here we need what is the name of the actual endpoint, but we will also need some context around the endpoint. So it is not enough just to have like a point name that says sensor 1, because obviously even as a human, you're not going to be able to know what the sensor 1 does if you don't have context around it. So some type of information is needed. For example, this sensor 1 describes indoor temperature in room X or whatever. So some context is needed. And then we also need some source URLs from where to actually fetch the data through like an API if there is one. And then our agent updates the model configuration file. So we update the actual mapping between the resource and the endpoint, and it'll also update in the source of where to find the data. And once that model is updated, or the configuration file is updated, then is pushed forward towards the next agent. And here's kind of like the process flow of the whole agent, kind of like how it is going through this first task. And the first thing that it actually does, it reads the files that we give it to. So it'll read the input. So what we have in the Finnish pilot, we have the resource endpoints just in a .csv file, and then we have the model configuration file that is something that is defined by the model developer. And in here, you can see what the actual model is supposed to do, and then we have the features for the actual model. So it'll have a description or the actual name, what the description is, and then the source field is empty. So that's what our agent will then update once the mapping is done. So then in the mapping node, the agent will actually analyze both the resource endpoints and it will analyze the model features and then provide a mapping between the two. And here's an example of what we have at the moment. So for example, from the model, we can find a feature that is called tank temp bottom, and then it will suggest this as a match from the resource. And you'll have options to just accept it. You can also choose additional candidates, or you can provide keywords if this is not the best possible match. And to kind of improve the mappings over time, this agent is also connected. It'll have persistent memory of the previous accepted mappings that it can use to kind of guide any future mappings. So what it's actually done here is that it's connected to a database, and when it's providing this mapping, it can check into the database and see if there has been any similar types of mappings before and use those to guide any new mappings that it might have not seen before. And once the mapping is accepted, it'll go through a similar process through the URLs to kind of pick the correct URL on where to find the data, and then it will update the model configuration file. So in the model configuration file, it will just update the actual source on where to find the data, and then going further, our API or the model can then just go into this URL and read the data that comes out of the resource. And this process is then kind of like repeated over any of the features that we have in our actual optimization model. And once everything is gone through, the agent will export the model configuration file, and then push it forward to the next agent for the semantic alignment with the serif ontology. So that's an example of one of the agents that we have in our LLM tool. So then as a summary of my presentation here, so why we need this automated integration is really the fact that for any of the work that any of us are doing, we need a large-scale deployment of these renewable distributed energy resources. And to actually do that deployment and integrate it into these systems, it's a lot of hours, it's a lot of manpower. So anything that we can do to kind of help and automate that process will make it easier for us to deploy these resources. And again, the approach that we have in Independent is to try to automate this process through this LLM-based generation of the semantic adapters that will then connect the resources into their managers. Okay. I think that's everything. Thank you.
I would like to invite you for any questions. There is one, please.
Thank you so much for the presentation.
Yep.
I found it indeed very enlightening. I would like to ask you a twofold question. The first one concerns compliance, and another one LLMs. As we know, the European Union is notorious on legislation, and it was mentioned in the slide that, for example, when it comes to the aggregated energy management system, the full GDPR compliance is assured. As I was observing your presentation, it seems that the automation reaches the level where also the EU AI Act also becomes relevant.
Yep.
And so I wanted to ask you, how do you go about this matter? You for sure assure the GDPR, but also a bunch of other acts also come into play. That's the first question. And the other one, when it comes to LLMs, it seems that it's quite complex coding activity. Is it your specialists themselves who develop these complex modules and scripts? Thank you so much.
Yep. So first of all, regarding the EU AI Act, yes, that is a concern because obviously we're working in a case where we have critical infrastructure, and we are using data that comes from critical infrastructure. So it is still a little bit of an open question on how can we actually address it. And I think I might not be the best person to answer that question. Maybe there's someone who's a little bit more legally better versed than I am. But it is a real concern in any cases where we use AI and large language models in terms of critical infrastructure, and how do we actually ensure that we're doing this safely and comply with everything that is in there. And then the second question regarding the LLM stuff, yes, that is kind of like my focus area, and it is a complex process, yes, but that is kind of like what my main focus is within this project. Yep.
Maybe from my side, I'm wondering, how do you validate the adapter? Like, okay, you train it somehow, and then for the research purpose, I can imagine that you can do it manually, but in reality, like if you would use it for purposes of this, you would like to avoid this check, right? So,
Yes.
So how you validate the correctness of the alignment, let's say?
Yeah, that's a good question. So right now, the adapter is being developed within the Finnish pilot, and the plan is to then try to apply it in the other pilot projects as well. But with large language models, there are very few ways to actually kind of verify the output and ensure that they're actually doing what they're supposed to be doing. So what we have right now is a human-in-the-loop method. So for the mapping between the resource and the optimization model, it is always a human-approved mapping, just because there the mapping is maybe slightly more critical than, for example, aligning with the serif ontology. So in there, the plan is to use like some type of a confidence score. And then if the mapping is given a confidence score below a specific threshold, then it'll be a human approved mapping. But right now we're using a human in the loop method, but there, like even going forward, there needs to be some like concrete ways to actually evaluate the decisions that these LLMs are making. And specifically in the energy domain, there are very few applications of these, at least what I've seen.
And just maybe correct me if I'm wrong, but I understood that this LM, it's something like this kind of localized open source LM. It's not nothing like ChatGPT or something like that. It's kind of the focused LM, or do you use this kind of large language model?
But for these ones are using general LLMs. They have enough base knowledge to use for cases like this. And it would be possible to fine tune these, but again, that needs high quality specific data. So I think if there is enough context to provide from your resources and from the ontologies, then the general purpose LLMs will be good enough for this task.
I would like to thank you.
Thank you.
It would be great.